Okay, I thought you might like a little help on the friction problem. Let's take a look at this again. We're using one of our main go-tos here is that net force is equal to mass times acceleration. We also have our equations that say that the force of friction, if it's kinetic friction, it's going to be mu k, which is our coefficient of kinetic friction, times the normal force. And if it is, and I'll put Fk here, and Fs here for kinetic friction. This is our kinetic friction, this is our static friction, and we would use mu s times Fn. Okay. And maybe one other equation here, that force due to weight or gravitational force is m times g. Okay, so let's see how this problem goes. First of all, the first problem we're going to do is, what does the sled weigh? So when we're talking about weight, we are obviously talking about this equation right here that says that the weight force is equal to the mass times gravity, or acceleration due to gravity, which will be equal to, according to our problem, 50 kilograms times 9.8 meters per second squared. Okay? And this just equals, I believe, around 490 newtons. Okay, so what force will be needed to start the sled? Let's draw ourselves a free body diagram, which we should always do. We know that on this sled, there is the force of gravity pulling down, which is also referred to as our weight, which is also what we know to be is m times g. This is very good because we already in part A found out that m times g is just 50 times 9.8. Then likewise we know that this has to be counterbalanced by the normal force. Since this sled is not floating in the air and it's not sinking into the ground, then the normal force, this vector right here, must be equal to the vector going down the gravity force. So that means that Fn is equal to Fg, which means that it's equal to mass times acceleration due to gravity, which again is 50 times 9.8. Well, that's nice. So now we know what those two things are. But the question asks us, what force will be needed to start the sled moving? So that means that we want the force to go in this direction. So we have to apply some kind of force, a push or a pull. I'm going to put A for just applied force. That way it can be either one. And in order to start the sled moving, I have to overcome the force of friction. In this case, B says the force needed to start the sled moving. That means that the sled was not moving to begin with, which means that we are looking in part B, we are looking for the force of static friction. So we will need to use mu s times the normal force. Well, looking at our diagram here, we see that that the mu s, actually the mu s is given to us right here. Static coefficient of static friction is 0.3, and our Fn, which is right here, here's our Fn where we're getting this from, is actually just 50 times 9.8. Okay? You can go ahead and get that answer. It'll be in newtons. Part C says, what is the force to keep the sled moving? So it has started moving, and we are then going to go to the force of kinetic friction, which will just equal mu k times Fn, which we already, again, as in Part B, we already know what that is. Our mu k is given to us up in the problem. It's 0.1, and that will also be times 50 times 9.8. And you will have to figure that out on your calculator, put in the newtons. So that leads us with D. D wants to know, once this sled is moving, what if I wanted to accelerate to 3 meters per second squared? So let's think about this. Now what we're saying is, I have my force of weight, my weight force, I have my normal force, I still have my friction force, but I now want to make a bigger applied force so that I have a net force that causes an acceleration to be 3 meters per second squared. So let's take a look at this. We know that our net force is equal to mass times acceleration. And what this problem is saying, that when I add this force together with this force, my net force is going to be equal to, or my net force is going to give me an acceleration equal to 3. So what that is saying is that my net force is actually going to be equal to whatever the mass is times 3. Well, I know what the mass of this object is. It's 50. So that means that my net force is 50 kilograms times my 3 meters per second squared. I really should put in my units. Which means that my net force, when it is accelerating at 3 meters per second, is equal to 150 newtons. But that wasn't the question. The question was, what is the total force that I have to apply? They want to know, what is this right here? So let's take a look at this. Let's set up our equation for net force. Our net force has to be equal to the applied force, so we're going to say that's the positive direction, minus the force of friction. So putting in what I know I just figured out that my net force, when it is going at 3, when it has an acceleration of 3 meters per second squared, is 150. I know that my applied force, Fa, is equal to the mass of the object times the acceleration minus my force of kinetic friction, which I already got up here in C. So that's going to be minus the quantity 0.1 times 50 times 9.8. Okay. So my question is, what would be the acceleration associated with this applied force? I do know my mass, so that means that 150 is going to equal my mass, which is 50 kilograms, times my acceleration, minus 0.1 times 50 times 9.8. So if I now solve for acceleration here, and the way I would solve for acceleration here is to take 150, all right, and I would have to add 0.1, whatever this comes out to be, and then I would have to divide it by 50. That will give me my acceleration. Then whatever number that this acceleration comes out to be, I will put it back into the equation that F equals ma, and that will give me what my force has to be. I'll let you guys do the math and come up with it. I hope that gives you some help. Thank you. Bye-bye.